What are the primary differences between earthquake engineering and then traditional structural engineering?
I believe the differences lie in the focus on the design considerations and analytical approaches for these two. Actually, earthquake engineering is a specialized subdiscipline of the structural engineering practice, and it means that everything that a traditional structural engineer should know about the design procedure, material behavior, load combination, everything.
When it comes to designing and building safe structures, traditional structural engineering has been the go-to approach for centuries. However, as you've learned from devastating earthquakes over the years, traditional methods often fall short in the face of seismic activity. That's why earthquake engineering has emerged as a specialized field focused on mitigating the impact of earthquakes on buildings and infrastructure. Join us in today's episode as we speak to Reyhaneh Navabzadeh, Ph.D. and engineer at Structural Integrity Associates, about how earthquake engineering addresses these critical challenges, its key differences from traditional structural engineering, and innovative strategies for building safer, more resilient structures. I'm your co-host, Matt Cardle.
And I'm your co-host, Rachel Holland, and this is the Structural Engineering Channel.
Reyhaneh, thanks so much for joining us today. Can you tell us about yourself and what inspired you to pursue both structural and earthquake engineering?
Sure. Thank you so much for having me. I am Reyhaneh Navabzadeh, and I am with Structural Integrity Associates. We are a consulting company working mostly on energy and infrastructures part of job. And I got my master and bachelor degree from Iran and my PhD from Texas A&M University. My journey to structural engineering started because of my love to mathematics, physics, and creature. But I got into the earthquake engineering actually because of my personal experiences. I am originally from southeastern Iran, which is a very high seismic risk and active, region. And I have experienced a few major earthquakes, such as BAM earthquake in 2003. And that actually affected me a lot. And I wanted to pursue my study in earthquake engineering to know more about this, inevitable event and be part of the global efforts to reduce the risk and reduce the impact on people. Earthquakes are tricky because they are not just natural forces that are applied to the structures. They are really dependent to the structure itself. And if we have a structure with more weight, it will get more seismic forces. So to me, being part of the resilient design practice is very important, and I'm especially interested in some kind of multi-hazard analysis, like combining wind and seismic loads together for especially renewable energy structures, which is a trend these days to moving forward more sustainable cities.
Interesting. We had 3 earthquakes here yesterday in the Bay Area that people felt. So,
Oh,
and I've definitely lived through a couple of big ones as well. So it can be kind of life-changing, right? What
yes.
are the primary differences between earthquake engineering and then traditional structural engineering?
I believe the differences lie in the focus on the design considerations and analytical approaches for these two. Actually, earthquake engineering is a specialized subdiscipline of the structural engineering practice, and it means that everything that traditional structural engineer should know about the design procedure, material behavior, load combination, everything are required for a seismic engineer as well. But in addition to that, because earthquake engineering is adding one layer toward the resilient design practice, and which is adding the seismic load to the formulation, because earthquake and ground motions are different type of loads from gravity loads or wind loads that are mostly used in the traditional structural engineering. And an earthquake engineer should know about seismology, should know about the soil and the structure interactions, the dynamic behavior of the, structures, some concepts like mode shapes, frequencies, ductility. These kind of concepts are required for an engineer in the practice of earthquake engineering. And that will add more, kind of analytical approaches. We need to know about more nonlinear dynamic, analysis or response spectrum analysis. These are not just like traditional static, linear, or nonlinear kind of analysis that we use. And this again results in having more criteria, more detailed and different specifications than traditional structural engineering.
That's interesting. So you said you got your master's at Texas A&M, and then I went to Cal Poly SLO, and Matt, you were where'd you do
Cal Poly
yours?
Pomona and UC San Diego for my
Okay.
master's. Mm-hmm.
So it's funny because we studied all of like the earthquake part, but we're in California. So are there like structural engineering programs out there that just don't study that at all? Am I naive in thinking that the earthquake aspect of it?
I believe it is really depends on the location. For example, in Iran, earthquakes are always the dominant kind of design loads. So even the design criteria has been, adjust and modified to that. So everything should be designed against earthquake.
Right.
And we don't do, for example, timber kind of building in Iran. I think it really depends on the location. And you said California, both of you have been here. So I think it really depends. I know that in Texas, for example, there isn't that much about earthquake and seismic design. It is about pre-stress design, the different kind of material kind of the study.
Yeah, I mean, I know it doesn't come up in practice as often, but I think I just assumed that all the programs studied it. Mm-hmm. So that's totally interesting.
I think it could be more detailed or less detailed.
Right.
Yeah.
I'm guessing East Coast probably wind. I'm guessing, but that would make sense.
Yeah.
But there are there are seismic regions like randomly where you don't always think of like seismic. So I think that's why I just assumed that all kind of educational programs studied both, but it would make sense. It's to different degrees. So totally makes sense. What about with global standards and practices? You mentioned how obviously the stuff in Iran is very much so focused on the seismic parts.
Yes.
How have the global standards and practices in earthquake engineering evolved? And then what strategies can be applied to the different regions with the varying seismic risks?
I think at the beginning, there wasn't any seismic design included in the codes because it was not a very familiar kind of load. And eventually it was added to the codes, but it was a very conservative code-based kind of, requirements. And there is a thing about the seismic specification that they are really evolved through the lesson learned from past experience. Whenever there was a big, kind of earthquake, then after that, provisions has been adopted and modified again and again. I know that, for example, Japan and New Zealand are considered as pioneered in using the seismic design. But let me focus on just US for now. I think that it was just around 1960s that they started to talk about seismic design in the codes. And they mention it in UBC, for example, in 1963, but still it was not a very, suggested practice. But after several earthquakes during the 1970s and 1990s, they started to talk about the ductility and performance-based design. This concept were introduced very well in a provision. I think it was called Vision 2000, and it was released on 1996. So that was actually the very first report that required the seismic standard for California. And after that, as I said, each year they are improving the seismic provisions, and they call it state of the art, which is, I believe, 10 or 15 years ahead of a state of practice, what we see in the codes. And there are ongoing research and studies on everything that should be in the next revision of the specification. Excuse me, would you please repeat your second part of the question?
Yeah, I just was curious about the strategies that we can apply to the different regions with, depending upon their seismic risk.
Yes, and as the provisions are improving, there are still technologies, new materials, new innovation ideas. So I think everything is improving based on that. For example, using smart materials, using base isolation, applying this performance-based design criteria in different type of structures. And I think, but in general, it is really depends on the risk in every region. We can separate the region into low, moderate, and high risk regions and apply different strategies. But in general, I think the strategy should be in policy making, in design, construction, and utilization of structures, and in 3 steps: pre-earthquake, during the earthquake, and after that, post-earthquake, regarding the loss estimation, the mitigation programs, or the lesson learned from the earthquake.
Yeah, I know our codes are always getting updated with, for me, looking at building codes every couple of years, you'll see a new section, for example. Yes. I think there are some new ones for egress stairs. Yes. Where you either have to take them into account to the building or isolate them from floor to floor. And I think that came from some photos of egress stairs just getting completely demolished during an earthquake and no one could escape the building.
Yeah.
And it's always in the commentary. So that's really interesting to see how, hey, there's a new section of the code. What was it inspired by? Either by new research or, as you were mentioning, just from lessons learned out into the field after earthquake happens.
Yes.
And I think it's interesting too how you mentioned how they call it state of the art versus state of the practice, right? Because even like once it is in the code or like the IBC, there's always that lag. And then that's even like there's more of a lag in certain areas, right? Like certain jurisdictions, like there's so much of a gap to like, yes. When have they adopted it? When are they actually enforcing it?
Yes.
So it's pretty wild that it can be there's such a big.
Yes.
And the code books keep getting bigger and bigger. So I wonder how big it'll get.
Yeah. For example, I know that the first ACI that was mentioning seismic, it was about 60 pages. It was in 1971. And then today's ACI is about 600 pages. Of course, it has a lot of other, things, but seismic is a big part of that.
Yeah.
And besides the code books, what are some of the most pressing challenges earthquake engineers face today, and how do these influence the design and implementation of the seismic resisting structures?
I think one of the biggest challenges is that the cities are getting bigger and bigger, and there are a lot of metropolitan and big cities that are located on the high seismic risk regions, and we have different kind of structures over there. We have underground structure, underwater structures, tall rises, everything, and energy storage facilities. These kind of things all need their own specific criteria. So meeting the seismic criteria for all of them would be, I think, very challenging and expensive. And I can think of that, for example, today's with the wind energy and the increasing number of wind farms. These structures require their own, criteria, because it's a totally different kind of a structure from whatever we had, residential or even tall buildings. The second thing is, I think seismic requirements should be applied to both new building and existing buildings. And there are a lot of old structures or historic landmarks that should be saved from earthquakes. And they need their own different, criteria. One of the beautiful examples that I like it very much is the Golden Gate. I am always admired by that because it has been a structure that was built in 1913s, and there was no seismic criteria back then. And it has experienced a lot of big earthquakes. It survived, but not because of the seismic design, but because of the kind of suspension and flexible structure that it is, that could absorb the seismic force as well. But after for example, one of the biggest earthquakes, Loma Prieta, in 1989, they realized that it needs to be retrofitted for seismic provisions as well. And they did a great job by retrofitting the piers, the structure itself, the cables, and installing the sensors for monitoring the behavior of the structure. So this is another challenge. One of the most recent challenges that I can think of is the climate change. It is not just affecting the daily life of people, but because one of the most important things in earthquake engineering is the soil and structure interactions. Every change in the soil properties will change the risk at a location, seismic risk as a location. For example, with this kind of flood that washing away the water or changing the groundwater level, those will affect the soil in that areas. And another example is multi-hazard regions. For example, California is both seismic and has both earthquake and wildfires. And the criteria should be updated for this kind of multi-hazard events as well. How we can have safe buildings and structures against fire when we are using light woods to reduce the earthquake, loads. There should be some modification between these.
What about, you talked about a couple of those things that have happened in, recent history for making advancements, but what about in terms of you mentioned this earlier too, but new materials are constantly coming out and things like that. So
yeah,
what about recent advancements in anything like materials, technologies, research, all of them? How are those shaping structural and earthquake engineering practices?
Sure. There is this concept of smart material that they are used in, for example, dampers or connections or bracing system to absorb seismic energy and dissipate energy. For example, shape memory alloys. These materials are used in the concept of adaptive structures. Adaptive structure means that they will go back to the original properties and situation that they have after the unloading, and with minimum residual deformation, which
what
is
are
very
when you're talking about those, I haven't heard a lot about those yet. Or is it like a specific type of building material that has that property, or is it its own material?
Would you please explain more?
Like when you're talking about the shape, what are you calling them? Shape?
It is shape memory alloy. I think it is some kind of thing that should be added.
So it's like a part of the metal mixture when they're creating steel or something like that? Okay.
Yes.
Okay, perfect. Thanks.
Yeah, you're welcome. And there are also fiber reinforced concrete or polymers that are adding to the material for more flexibility and more strength. And there's also, for example, base isolation concept that are separating. These base isolation is used to separate the foundation from the structure itself, and that will reduce the amount of seismic load that is affect the structural system. Or we have dampers with the different concept of active or passive kind of dampers. Another topic that should be considered is the sustainable solution that we have. Structural health monitoring and digital twin. These two concepts are very hot topic these days because they can provide real-time data of the structure for you, and then you can apply it to the simulation and models that you have and get real responses from the structure, and it could be used in predicting the structural behavior, or even detecting the ongoing damages on the structures, or predicted the failure at a specific component of the structures. So this is another innovation. There is another thing that I can mention. It is more related to the seismology part of the earthquake engineering. It is not a certain and reliable way to predict when an earthquake will happen and where it will happen, but there are progress in some kind of sending early alerts to the people in the region when the earthquake happens. For example, this system is active in Japan, or there is one in Mexico, and recently we have shake alert in California, which can detect the earthquake waves when it happens, and even in seconds after that, and then issue the alert to the people.
Is that something that you have to like sign up for? I'm like, why do I not have that? I feel like even when I feel an earthquake, I go to USGS really quickly, and then it takes a few minutes to populate,
I believe there is an app for that.
Okay. Actually, you know what? All of a sudden, now that you say that, I feel like I have the app. Maybe I should just open it. Okay.
And I didn't receive that myself, but I hear that for the previous big earthquake a few months ago, people in Bay Area received the alert on their iPhones. I don't know.
Maybe I did, and I just don't remember, but that's good. I'll try to remember that more.
Yeah. So I think it's a very cool thing. It shows that we are progressing toward what really needed. And I believe with AI and this machine learning progress, that is a very hot topic these days, at some day we would be able to predict at least the location of the earthquake,
I just looked. The app that I have is called My Shake. Is that different than the one you're talking about?
The one that I can remember was Shake Alert.
Okay. I'll download that one out.
Maybe there are a lot.
Yeah, I'm guessing there might be different ones.
Yeah.
Yes.
Okay.
Yes. And Other than that, I think there are a lot of undergoing research about the soil properties because, for example, one of the big and famous aspect of earthquakes are liquefaction, and it is really depends on the soil properties and the effect of earthquake on the soil of a region. There are good examples that the structure itself was very well designed for the earthquake loads, but according to the liquefaction, it was just washed away and it has been destroyed. So there are a lot of research on that area as well about the soil stabilization and this kind of practices.
Yeah, there was a lot of good stuff in there. Like I think the ones that stood out for me were the smart materials. Where it is. Like, I know we'll get into the resilience and whatnot, but from what I've seen, if your structure doesn't have those types of or those, I guess maybe self-centering or smart materials, they just may be literally bent out of shape because they're leaning, and no one wants to live in a leaning building.
Yes.
But with those types of materials, when we get into resiliency, if it shakes and it goes back to position, great.
Yeah.
And people can still live there with minimal damage.
Yes.
And what strategies do you recommend? Because of all these new technologies, there's probably that balance, right? For like, how do you balance the resiliency, functionality, and cost when designing these types of structures in seismic regions?
I think the big key is the efficiency, and it means that we should maximize the function of the building while we are minimizing the unnecessary expenses. And it can be achieved through optimization design, going through the cost-effective material. It means that if we use the locally available material, which has been passed the test for resiliency, that would be a very good approach. If we can have some kind of smart, construction approaches, like using symmetric and prefabricated units that has been designed for earthquake. Or we should have efficient retrofitting. It means that we should have targeted retrofitting for example, that specific location that has been damaged. Or we should use the sustainable material for retrofitting, like low carbon concrete or recycled steel, this kind of material. And also, a big thing is having supportive policies and training from the policymakers to deal with, the seismic criteria. And because it is, of course, it is not affordable for everyone to do that, but sometimes paying much more at the beginning is very, beneficial to having a lot of damages or loss at the end.
Yeah, for sure. It's funny how you mentioned like the policy, just the policy making. I feel like that's come up a few times in our conversation. And I always find that to be really interesting because when you're a young person and you're going to school, you're like thinking about designing buildings and doing all these things. And you never really think about having to take it to that next level where you have to like take all this information that and it's like very technical information, and preach that in a way that like policymakers understand its value and its worth, and then follow it through to have it actually like implemented. It's like this whole other avenue of our field that I don't think we talk about it a lot as young people.
No. For example, this performance-based design actually is a good example, because you can define what do you need from your structure. You like to have it operational during the earthquake. You want to have it as an immediate occupancy after the earthquake, or life safety, or just collapse prevention. And all of these stages require its own criteria. And one of the things that policymakers and investors do is that they decide which one they want to have. for that structure. And based on that, everything would change.
Yeah. Yeah. It's really interesting. And even like a lot of like what I do in my role is we're out talking to people about how to build, code compliant structures. And we talk a lot about how, like, we kind of stress that, when you build a code compliant structure nowadays in California, like, that's a life safety structure.
Yes.
Like,
yes.
So, and people, I think, just, general population, they don't understand that.
Yes.
Like, that's not a concept that's really like a general concept.
Yeah.
Yeah. It's like the code compliant means bare minimum.
Yes.
After an earthquake, you may need to tear it down.
Yeah.
But yeah. Opening it up or getting the public to know more about, the performance-based design aspects. You can choose what level you want, right? So it's out there. Or I guess it's fairly new in terms of a couple decades. But yeah, it's like we have the technology to do that, and we can, and it's making the public more aware of their choices for their buildings.
Right.
And what about like if for regions that are resource limited? I'm not sure if Iran is, or maybe some other countries. Like, are there more practical methods to get these types of earthquake resistant systems implemented more in these types of countries?
I think the very first step for every seismic region is to macrozonation. I mean, to do the research and study to have different regions with different seismic risk that we have, and based on that, then they can continue and apply the regulations. But it is not very affordable for all of the countries, as you said. I think this is the most important thing that should be done at the beginning. And of course, you cannot use the, for example, seismic map of one country to another country. It is something, unique for
Specific.
each country.
Yeah.
You should do that. But the thing that you can do is adopting the well-established criteria around the world, and then customize it based on your own region and the properties and, for example, local materials that they are available over there. This kind of codes like A.M.ASCE 7 or Japan guidelines, they can be used as the, a starting point master, and then be updated based on the whatever you have in your region. Another thing that I can think of is I think education is very important for both builders, local builders, and people, because by education you can at least minimize the life loss after an earthquake, or you can, teach them how they should react to an earthquake, if even they know that the building is going to be damaged, but they can save their lives. And another thing is that is very important is the support from the NGOs or investors that should invest in those countries and help to improve the criteria over there.
I think one advantage that we have right now is that we have become such an international world, right? Like before we were so like separated and it was hard to share that information. But like as we make advancements here in the US, like we can put out publications and other countries can use that. And same thing with like Japan. They've done all these advancements. They have their guidelines. And then other countries have the ability to look at those and be like, should we also update ours to reflect what they've learned, So the ability to share that information, I feel like it's really helping us to like exponentially increase how much better we can get in a shorter amount of time. So that's advantageous.
Yes.
What about in terms of skills? Like we talked about, you just mentioned education, but what do you think are like the most important skills, or maybe like a specific area of knowledge that engineers should try to develop if they want to excel in earthquake engineering?
Mm-hmm. As I mentioned before, because earthquake engineering is the sub discipline of the structural engineering, every earthquake engineer should know about the basics of design, material behavior, structural analysis, these kind of things. But the most important for them is to know about the earthquake themselves as well. I mean, earthquake engineers should be able to process the ground motions and should be familiar with how we are, for example, driving the response spectrum or the design spectrum. These are or how we are processing the ground motions, because when you are given a set of earthquakes to be worked with, you should be able to understand if, for example, this spectra looks good or not. It is like, doing the hand calculation for the base shear. It is basic that you should be able to do that. And I don't say that we should be expert in every aspects of the earthquake engineering, but at least we should be up to date and know what that we are working on, and it is very important to know about the different kind of analytic approaches that we have, getting familiar with this computational and finite element simulations, for example, nonlinear time history analysis. It's very important. um, some topics like risk assessment or for example, damage detection, fragility curves, these kind of things are going all after the earthquake, post-earthquake, but these are required for an earthquake engineer, to understand the real behavior of this structure. I would say if it is possible for an engineer to do the site visit after an earthquake, that would be very, helpful. It is sad, but it is, as I said before, it would be learned from past, and you will see, okay, this, for example, this structure was supposed to be designed for immediate occupancy, but now it has been collapsed. What happened? What was missed here? And I remember that when BAM earthquake in 2003 happened, I was undergrad student, and I saw the pictures that they did a lot of wrong connection, and I was thinking, okay, these are not what we have read in our books. This is not what we are supposed to do. And after the earthquake, you see, okay, what happened there? I think there should be a very strong supervision in the construction process. Sometimes the design engineer did their job very well, but there isn't any supervision on the construction part and building part, and a lot of things has been missed.
Or it was designed to a code that we didn't know yet. We just didn't know. The information wasn't available. So
yeah, like in California, I think sometimes we take it for granted. Even just taking, I think getting a building, designed and built, it's a long process where there's inspectors and lots of people are, sometimes frustrated because the process takes so long.
Yeah.
But if everything goes well, I mean, there's a reason why there's inspectors and they won't let them build something unless it's up to par. And I think that's something that we take for granted sometimes, where it's like, sometimes it's a pain just to get it built. But I mean, when an earthquake hits, it works. So Reyhaneh, what's some of what final piece of advice can you give to earthquake engineers or structural engineers looking to specialize in earthquake engineering, or maybe integrate some of their seismic design principles in their work?
Once someone told me that earthquake engineering and structural engineering are finished. We don't have anything else to work on. Everything is out there, and okay, we are done. But I don't think so. With all the challenges and new things that are happening, I think if someone is really interested in earthquake engineering, they should be engaged and proactive and never stop learning, because there are always things to learn. For example, these new materials, new technologies, climate change that bring a lot of new challenges to our, life. I think the best thing is to be involved in both sides of the industry and research, and to be engaged. For example, they can be part of a technical committee and participate in that kind of activity. As an engineer with a company, you can, bring some real engineering problem to those kind of research centers, and they might have the knowledge, but you can be the translator, to make it a practical idea. And keep yourself up to date. There are a lot of organizations like Earthquake Engineering Research Institute or other organizations that are having different kind of technical seminars, workshops, or conferences. And it's always good to be a member to have access to those information, and never stop learning.
All right. Well, awesome. Thank you so much. It was great to meet you. And thanks for joining us today.
Same here.
Thanks so much.
Thank you very much. Thank you.
I hope you enjoyed the episode today. We'd love to hear your feedback, comments, and or questions. To leave them, please visit structuralengineeringchannel.com. There you'll find a summary of the key points discussed in today's episode, as well as links to any of the resources or websites mentioned during this episode. Don't forget to subscribe to Apple Podcasts, Spotify, or wherever you listen to your podcast. Until next time, we wish you the best in all of your structural engineering endeavors.